In this video, we introduced the concept of power spectral density for a stationary random process. Now let's review the power for a deterministic signal. Deterministic signal means that there is no random variables involved in the signal. So we know that power, we take the time goes to infinity. We do integral from 0 to t, and then x of t magnitude squared of dt. So this is the power definition for our signal if the signal is deterministic. Now, how do we measure the power if the signal involved with random variable? And this signal become a random process if random variable involved. So that's where the power spectral density come into the play. Power spectral density is we take the Fourier transform of the autocorrelation. Remember, for a stationary process, the autocorrelation is a function of tau. Tau is a time, so we can take the Fourier transform. So now if I take the Fourier transform, and this is a Fourier transform definition, this is a time domain signal, we take e to power minus j 2 pi of tau and an integral by tau. So this is a Fourier transform, and this is the power spectral density for the stationary process x of t. The notation is a power spectrum. Yes, Ex is a random process, and F, that's a function of the frequency. The unit of EXF is watts per hertz, so therefore it's a power spectral density. Remember, EFX is not the Fourier transform of EXT, it's a Fourier transform of the autocorrelation of the random process. Because of this is a random process, we do not take directly the Fourier transform of this random process. Let's look at the power of the random process, and also sometimes people call it total power. Is the summation of the power in all the frequency in the frequency domain. We really integral from minus infinity to infinity. We take this power spectral density, and this is the power or the total power contained in this random process. What is this equals to? This is equals to Rx at tau equals 0. If tau equals 0, Rx 0 is really expectation of xt multiplied by xt again. Now, if we compare the definition of the power of deterministic signal with the power of a random process, you can see here, you take the signal's magnitude squared. Now you take the same signal squared, you take expectation, and here we take the integral, you take the time average. So this is a power for deterministic signal, and this is a power for the random process. If we look at R tau is the inverse Fourier transform. So we integral the power spectral density and complex exponential e to the power j 2 pi of tau do integral on f. So therefore, we obtain the function of tau, and this is a time domain. So this is a time domain, and this is a frequency domain. Okay, so this is a Fourier transform pair. This is a Fourier transform, and this is time domain signal here. Tau equals 0, because tau equals 0, this signal is equals to 1. This is 0. So therefore, we have this integral, this whole integral equals to Rx 0. So let's look at the example here. We know this random process is stationary, and we know Rx equals to a squared cosine 2 pi f naught t1 minus t2, that's tau. So T1 minus T2 equals 10. So therefore, if we take Fourier transform of the autocorrelation, we obtain the power spectral density. What do we have? We have, this is cosine, right? You have a squared divided by 4 and 2/3 functions at f naught and minus f naught. So this is power spectral density. If we want to obtain the power, what is the power for this random process? What's the power for this random process? And we have two ways to obtain here. Px equals to Rx 0. That's here when tau equals to 0. That equals to a squared divided by 2. Or we do integral of the power spectral density from minus infinity to infinity. And when we do this, we use the property of delta function. If we integral from minus infinity to infinity delta t and d of t, that equals to 1, right? Or delta t minus t naught, that also equals to 1. If we do integral, that's the same thing. If you shift it, if you do not shift it, that's the same thing. If we do the integral in frequency domain, this, the first delta integral from minus infinity to infinity delta function, that's 1. The second one is 1, so therefore we have 2 here. So therefore we have a squared divided by 2. So both ways we obtain the same results here. That's the same result. If we look at this signal, if theta is not random, it's deterministic, then what is the power for this cosine signal? That's a squared divided by 2. Everything agrees to each other. This is how we obtain the power of a random process using the autocorrelation or using the power spectral density. The power spectral density is a Fourier transform of autocorrelation, and autocorrelation is inverse Fourier transform of the power spectral density.